Today we're going to start section 7.2, which is operations on decimals. And in particular, we're going to take a look today at addition and subtraction to start with. So when we're talking about addition and subtraction of decimals, our basic idea is to line up the decimal point and then to do addition or subtraction as you would with any whole number, usually from right to left, although there are other ways to do it too. And I'd like to talk about why this works. Why is it appropriate to line up the decimal and for us to actually do it this way? And the example I'd like to consider is 4 and 33 hundredths plus 3 and 26 hundredths. And I'm going to break it completely apart just to sort of really verify the fact. But we have a 4, and then it says we have 33 hundredths, or we have 3 tenths and 3 hundredths. That's the individual place values that each digit is in. And adding to that, we have 3, and we have 2 tenths and 6 hundredths. So it looks like that. So kind of like when we were doing some different things with mixed numbers in the last section, we can add the whole pieces together. So that's 7. We can add the tenths together. 3 tenths and 2 tenths makes 5 tenths. And then we can add the hundredths together. 3 100ths and 6 100ths makes 9 100ths. And if we put that back into decimal form, we'd have 7 and 59 hundredths. And that's exactly what we have when we add them together as it's being described. 3 plus 6 is 9, 3 plus 2 is 5, and 4 plus 3 is 7. So it's all hinging back to the things that we did back in the last chapter with fractions. So that was an example without any context for addition. Let's actually do one with subtraction that does have some context, though. A stock's price dropped from $63.28 per share to $27.45 per share. What was the loss on a single share of this stock? So we would be subtracting this, right? And it's 63 and 28 hundredths minus 27 and 45 hundredths. All right, so the first piece is straightforward enough. I can do 8 minus 5 just fine. What do we get? 3. Good. The next one, though, I don't have enough to do the subtraction, right? 2 minus 4, and I don't have that much. So we're going to regroup, and that is sort of the prevailing phraseology right now in the schools is regrouping, not borrowing, just so you know. If you talk to a child and say borrowing, they might not always know what you're talking about. Regrouping. So the idea is that we're going to take that 3 and we're going to make it 2. We are borrowing. We're taking 1, in this case $1, and we're turning it into dimes. That would give me 10 dimes, plus the 2 dimes I already have, so I have 12 dimes. Okay, so I am regrouping the value. And then I have 12 minus 4. And 12 minus 4 is what? 8. Okay, I, once again, in a position where I can't subtract. I have 2 ones and I have 7 ones I'm trying to take away. So I'm going to take one of the 10s, right, taking like a $10 bill, taking one of them away. So now I have 5 $10 bills. And I take my 10 and I break it down into 10 ones plus the 2 ones that are already there. So now I have 12 ones. 12 minus 7 is 5. And lastly, 5 minus 2 is 3. Because this one has context, namely its dollar amount, we want to make sure that we have that as a part of our answer as well. So our answer is $35.83. Okay, is that good? So this is addition and subtraction. Interestingly enough, when we do fractions, multiplication and division is easier than addition and subtraction. And when we're using decimals, it's the addition and subtraction that's easier than the multiplication and division. So let's move into multiplication next and talk about why some of the sort of conventions that we use work. So multiplication, what we do is we multiply the way we would with whole numbers, and then we count the number of places after the decimal point in the numbers we multiplied. And this will be the number of places after the decimal point in your product. So if I do that for this particular problem, there's nothing about lining it up. This one happens to line up if I just stack them anyway, but it's not a necessary thing. We're going to do 7 times 3, which is 21, okay? So we're ignoring the decimal points. Everything else before that are zeros. It's really just like a 1 digit by 1 digit multiplication, 7 times 3. And then we count the number of places after the decimal. So here's 1 and here's 2. Okay, so the total number of values after decimal points, 1 and 2. So I have 2 decimal places, or 2 points after the decimal place. So here's going to be my decimal place so that I have 2 digits matching those afterwards. I don't think that that's necessarily difficult to remember to do, but it looks a little bit like magic, doesn't it? I mean, I just counted things up. I mean, I didn't like line them up. I didn't drop the decimal. There wasn't like this organized fashion like it felt like there really was with addition and subtraction. It feels a little mysterious. So let me show you why with fractions that this makes sense. So 3/10 as a fraction is written like so. And 7/10 as a fraction is written like that. And you guys know for multiplication with fractions, we multiply across the top, it's 21. Across the bottom, that's 100. 21 times 100 is 21/100ths in decimal form. That's what's happening to those place values to put 2 numbers after the decimal point. So it's really not magic at all. It still looks a little bit funny, but there's a reason behind why it works. All right. So let's take a look then at what happens when we talk about division. Because division also has sort of one of those kind of weird things that we do, and we may not necessarily know why. Division, we make the divisor, that's the number on the outside of the house, if you're thinking about it like that. We make the divisor into a whole number by moving the decimal point. And then however many times we move the decimal point in the divisor, we have to move the decimal point that many times in the dividend underneath, right? And then we divide like we would with whole numbers. So let me actually do that on this particular problem. This is 0.75, and it's being divided by 0.5. Okay, so we're actually going to do the process, and then we're going to justify why it works. So this says I should move the decimal point here so that I end up with a 5 as what I'm dividing by. And since I moved it 1 time here, I'm going to move it 1 time here. And I actually now have a decimal point sort of in between the 7 and the 5 on top of my division bar. Okay. And then I'm going to divide like I would normally. How many times does 5 go into 7? Once. 1 times 5 is 5. So I have 7 minus 5 will be 2. I'm going to bring down my 5. 5 goes into 25. 5 times. 5 times 25 is 25. And I have my remainder 0. So I'm done. So the answer is actually 1.5. Okay, so let's again look at why this really works. I'd like to write it in fraction form, and I don't mean fraction form like 0.75 over or 75 over 100. I'm going to write it as a fraction because it's division, like this. Okay? Is everybody good with that? Like that kind of a fraction. So it is perfectly acceptable, and it is a property of rational numbers that if I multiply a denominator and a numerator by the same value, it doesn't change the fraction, right? Absolutely. So when I do that, I end up getting a 5 in the denominator, and I end up getting a 7.5 in the numerator. And if you take a look, that's exactly what happened once I moved these, is I divided 7.5 by 5. Okay? So when I'm moving decimals correspondingly in a division problem, the real effect is that I'm actually multiplying by some power of 10. If I've moved it once, I've multiplied by 10 to the first, twice, 10 squared, and so on. So that's what's really happening behind the scenes. So oddly enough, one of my 6th grade children at home did a problem like this the other day, and I was really hoping she was going to ask me why it worked. And she didn't, and I was so sad. She just took my word for it and moved right on, and I thought, what a missed learning opportunity. But if you try and force them to learn that and they didn't want to know it, then you're probably not going to make a lot of good progress there. Okay. So another thing that we're going to take a look at in this section is scientific notation. The basic form for scientific notation is a times 10 to the n power. A is between 1 and 10. It could actually equal 1. It can't equal 10. So we're looking at a units digit value. It could have decimal points too, like it could be like 2.7 or something, but the 2, hence, is still between 1 and 10. N, the exponent, is an integer. Notice it doesn't say whole number, it does say integer, so it could be positive or it could be negative and still be considered a scientific notation form. I'm going to walk you through how we transfer between standard notation, that's how we normally write our numbers, and scientific notation. And it might look a little bit different than what you've seen in the past. I know I teach it a little bit differently. The reason that I do is because the way that I think it works best to explain it works whether you're going from scientific notation into standard or you're going backward from standard into scientific. And the way that it's typically taught about like moving things left and right, that sort of language reverses depending on whether you're moving in or out of scientific notation, and so I think that can be a little bit confusing. So let me show you what I'm talking about. So we're going to talk about standard numerals, the ones that we use typically speaking, and putting them into the scientific notation form. So what you're going to do is you're going to move the decimal point to create a value between 1 and 10. You count the number of moves that you made. If it's a positive exponent, that happens when you have a large number. And a negative exponent happens when you have a small number. And those words small and large are, of course, very relative terms. So you can see what I mean by them. I mean large is anything bigger than 10 and small is anything smaller than 1. Okay? So we're going to do an example, of course, so you can see how this works. The example that we have is 298,000. So that's a big number. Agreed? It's a big number. I mean, if somebody wanted to give you that much money, you wouldn't turn your nose up at it, would you? No, it's a lot of money. Okay, 298,000 is our value. If I want to put a decimal point somewhere in that number to create a number between 1 and 10, where would the decimal point go? Between what numbers? The 2 and the 9. So this is actually the number, ignoring of the rest of the zeros that come after it, that I would create if I did that. Does that make sense? Now, that means I'm putting it up here, right? And originally, I don't see a decimal point in this number. So where's the decimal located? Well, at the very end of all the digits. Okay? So I need to count how many places that original decimal point moved to now reside between the 2 and the 9. So it's 1, 2, 3, 4, and 5. It moved 5 places. So down here in my scientific notation, it's 2 times 10 to the 5th. And the only other thing I have to decide is whether that 5th exponent is positive or it's negative. Okay? Positive exponents correspond to large numbers. Negative exponents correspond to small numbers. What kind of number did I start with? A large one, right? We already talked about it. We want somebody to give us that much money. It's a large exponent. So my exponent is positive. And that would be the scientific notation for the number 298,000. We'll do one with a negative exponent in a moment, okay? Okay, so that's going from standard into scientific. Now we're going to go the other direction, from scientific into standard. So if you're going from scientific notation into standard notation, you will move the decimal point to the number of places indicated by the exponent. And just like we said before, a positive exponent means I'm going to have a large number. A negative exponent means I'm going to have a small number. So when I look at my answer at the end, it should correspond back to whatever type of exponent I was looking at in the problem to start with. So the scientific notation that I'm given is 3.2 times 10 to the negative fifth. Okay, so, whoops, this number, negative 5, or the 5 part, tells me I'm going to move it 5 places. Okay? It's negative, which means the number will get how? Will it get bigger or will it get smaller? It'll get smaller. So if I'm dealing with the number 3.2 and I want it to get smaller, which direction does the decimal point need to move? It's got to go to the left because that's how I get a smaller number. Now you may not know how many zeros you need, so just put some in there and then we're going to count 5 places because it was a 5. 1, 2, 3, 4, and there's 5. So I have a decimal point. I have 4 zeros, and then I have a 3, 2. If you would like to put a 0 in front of your decimal point, you can, right here, or you can leave it off. It is inconsequential, okay? Doesn't matter. That would be the standard notation for the original scientific notation that I started with. Now, pause with me for a moment, because I mean, like, we can talk all day, about different sort of ways that we can represent numbers and how we can write a different value. We can talk about fractions, we can talk about decimals, we can use scientific notation or standard notation, but there are places and times when scientific notation is used, and there are places and time when it's not used. So can you give me an example of where scientific notation is used? And don't just tell me science class, be specific. Like, what kind of a number? Izzy?
Is that Avogadro's number?
Yes, that is one. So do you know what that's counting for? Because I don't remember. It's the mass of something or the size of something?
I couldn't tell you. That's
Okay.
nothing I remember.
Okay, so I don't remember what it is, so let's just actually talk about this in a sense of mass. So when you're talking about very small particles like, protons and neutrons and electrons, those kind of things. It's been a long time since I had a science class, just so you know, so don't quiz me on any of this. Those are very small, right? Yeah, very small. So that's actually a place where scientific notation comes into play, because representing that without a whole bunch of decimal zeros and stuff like that starts to feel a little bit more manageable because of the way the numbers are represented. So yeah, we're talking about things like chemistry, right? That's a chemistry topic. What else? Can you think of a large example, a big number where we might want to use scientific notation? Ooh, measuring light years. So we have, so in economics, there's macroeconomics and microeconomics, right? You do the same thing in the sciences, right? You've got micro things where you're looking at something very, very small, right? Microbiology. And then you've got macro things where you're looking at like astronomy, right? So light years, distance from here to the sun, to the moon, to the whatever. I don't know what you want to use and measure, but things that are really, really big, and again, in a scientific fashion. So it wouldn't make sense if I asked you, for example, to create a problem in scientific notation and you talked about your bank account. Right? Doesn't make any sense. So there are definitely places and times where scientific notation is used, and places and times where it's definitely not, even if the numbers are very big or very small. Nobody talks about our national debt in scientific notation. They don't. They could. The numbers are very big. Right? But they don't do that, right? We just don't talk about it that way. All right, I want to give you one more example of scientific notation and how it sort of plays out. So this one right here asks us to write the result in scientific notation. And what you'll notice we have two numbers that are in scientific notation being multiplied. Now, it's all multiplication. I know there's parentheses here, but we also know that we're allowed to regroup things, right? So I'm allowed to regroup the 8 and the 6 together, and to regroup the powers of 10 together. That's allowed, and it makes sense to do so because they're easier to combine. What is 8 times 6? 48, thank you. And then once we get to that 10 to the 12th and 10 to the 15th, we're back in chapter 6, right? How do we combine those? We add their exponents. 12 plus 15 would be 27. Now, we are not done. Why not? 48 is bigger than 10. You're exactly right. This said that my result should be in scientific notation, and 48 is bigger than 10. So what do? Well, I know that it needs to be a 4.8, but I have to compensate for that, right? I can't just throw in a decimal somewhere and it actually not change something. It changed it. What did it do? Well, 48 was a big number, agreed? So I need my exponent to become bigger to compensate. It's 28 now because I moved the decimal one location. Moved to one location, so the exponent increased one location. If you had done, I think there's an example of a division one. Let me just make one up right now just so you can see it happen. Let's say that you had 2 times 10 to the 5th over, I think 5 will work. 5 times 10 to the, let's make it 7th. Okay, so you would do the same thing we just did before where you would sort of compare like pieces. 2 divided by 5 is actually as a decimal 0.4. So we're working in decimal form. And then I would subtract my exponents, so I'd have 10 to the negative 2. Right? This is what it would be. And it wouldn't be in scientific notation, this particular one, right? So what would I have to change the 0.4 into for it to be scientific notation? Just a 4, okay? But the number 0.4 was a small number to start with, right? So correspondingly now I need to make the exponent smaller, which would make it 10 to the negative 3rd, and I would take away 1 from the exponent instead of adding 1 to the exponent. So it can work both directions. The ones that you have will only end up affecting the decimal moving one place, so you don't have to worry about what happens if it moves it 2 places. Well, the same thing would hold, but I don't think there's anything that happens in your homeworks that way. Brooke.
So back to the standard general scientific notation. When
Yes.
It says that a positive exponent is larger than 10 and a negative is smaller than 1. So
Yes.
What about like the numbers between those? So like what if it's larger than 1 but smaller than 10?
Okay, so let's just say it wanted you to take the number 5 and write it in scientific notation. Well, then it would be 5 times 10 to the 0.
Okay.
Yeah, that's a really good question. Because 10 to the 0, anything to the 0 power is 1, right? So that's how we sort of can put it in that form. But I will say too, Brooke, that there never would be any need because that would obviously not have been a number that we would have needed to use scientific notation for, so you don't see this done. But that is technically what would happen. Mm-hmm. Any other questions? Okay, we're going to take a look a little bit at rounding then. Okay, this is estimation that we're talking about, and the first type of estimation that we are going to talk about is rounding to the nearest blank. There's just a blank there. Because you can fill it in with whatever place value you need or want. Rounding to the nearest tens, rounding to the nearest hundredths, rounding to the nearest millionths, whatever place value could go in the blank. So what you do is you find the location that you're wanting to round to, and then you look one value to the other side of it. If that number is 0 to 4, you round down. If the number is 5 to 9, you round up. Okay, and we'll do an example on number 5 with that in a second, but one more type of estimation before we get there. Front-end estimation. Front-end estimation uses the first value, or maybe sometimes the first couple of values, and you round off. Rounding off is actually the same thing as rounding down, just so you know. What that means is you simply change everything after that digit to zeros. You just wipe them out. Okay? So let's do example 5 so you can see how that would work. We're first on example 5 doing an example of simply rounding. So this one simply wants us to round on part A to the nearest 100. So I'm going to rewrite the digits every time just so that I can underline and mark on them and not have to keep going back to the same example above. This says 100, the nearest 100. The hundreds place is right there. It's where my 2 is, right? Okay, so I go to that place value and I look one digit to the right and it's a 0. Well, 0 is in that 0 to 4 range, so everything from that 0 after it gets rounded down to 0. So I end up with a 2 staying the same and everything else becoming 0, so I have 200. Okay, so now we're going to go to the nearest hundredth. So I have 203, 651 thousandths, and hundredth is the 5, right? So again, we go to the right side of that, the number 1. The number 1 is in that 0 to 4 range where I round things down. So the 5 never changes when I round down. It still stays a 5. It's the 1 and everything after it that would become a 0 or simply not be written since it's after the decimal point. So you could either write it like that or you could technically write a 0 where the 1 is. That would be fine too. And then what says to the nearest unit? Okay, so what number's in the units place? The 3. So we go to the one to the right, the 6. So the 6 says that I'm going to do what? Round up. So what happens is that this time the 3 actually will change. It will go up to the next place value, and then everything else still becomes zeros after that. So it's kind of like you're imagining that 203, pretend for a moment it's money just because it's easier to think about. Pretend you had $203.65 in your pocket. Well, that's between 203 and 204, right? So if I round up, I go to 204. If I round down, I go to 203. I'm not going to 202. I'm not going up to 207. It's always in between the two nearest values that I'm looking at, which means the number either stays the same or it goes 1 up. So this one's 204. Okay, so let me show you some examples of what happens when we're working with a computation problem with estimation. So there's 2 parts here. It says use A, rounding, and B, front-end estimation to estimate the following. Then perform the computation like for real, like with the actual digits, and see how close your estimates are. Okay, so it is not my favorite part of the book here because it doesn't tell you when it says use rounding what to round to. It's very ambiguous, right? It is. What do I round to? Do I round to the hundreds? Do I round to the tens? Do I round to the ones? Do I round to the tens? I don't know. I get to pick. Well, the whole point with estimation is to make the computations easier. Does that make sense? So it kind of depends on what the numbers are that you're looking at. So as we're looking at these numbers, it probably makes sense to round either to the tens place or the ones place. So let's do it to the tens, just because that's what we're choosing. And understand that if Gracie chooses on the test or the quiz or test or the homework or whatever, and Jackie chooses a different place value and it didn't tell you, then it's okay. There's more than one answer sometimes, okay? So we're gonna use this as the tens because we picked it. Well, I didn't let you guys have a choice, sorry. Maybe I should have. All right, so if we use the number 89 and 47 hundredths, and I'm rounding to the tens place, will the 8 stay at 8? Will the 8 become a 9? It will become a 9 because this 9 says round up. So this is 90. My other one, 32 and 16 hundredths. The 3, will the 3 stay a 3 or will the 3 become a 4? It'll stay a 3 because the digit after it's 2, which means it rounds down. So I have 30. 90 minus 30 is 60. So this is 1 rounding estimation. Okay? Part B is the front-end estimation. So FEE, front-end estimation. Front-end estimation, in order to compare these, we still have to use to the tens place. I mean, it doesn't make any sense to do one of them to the tens and one of them to the ones, okay? So once you pick the place value you want, you're going to do the same thing for A and B. So I'm rounding with front-end estimation, or I'm using front-end estimation with the tens place. So I'm still using the 8 and the 3. But the thing is, with front-end estimation, it doesn't matter what comes next. It's all zeroed out. So the 89 actually becomes an 80, and the 32 becomes a 30. No matter what comes next, you zero it out. 80 minus 30 is 50. That's front-end estimation. And then part C says, find it for real, not in those words. But we're doing the 89 and 47 hundredths minus 32 and 16 hundredths. And we'll subtract as in with whole numbers. We'll start on the right-hand side. 7 minus 6 is 1. 4 minus 1, 3. I have my decimal point that comes straight down. 9 minus 2, 7. And 8 minus 3, 5. 5731. So if you're looking at the estimations, they're neither one like insanely far off, right? I mean, they're both in the ballpark. It's between the two. It's not always between the two, by the way. It wouldn't have to be. It could actually be significantly closer to one, or way bigger than both, or way smaller than both. I think that's a possibility. But on this one, it's a reasonably close estimate. Okay? All right. This is an interesting question. So here's what we're going to do. We're going to do example 7. I'm not going to make this due tonight. You're welcome. Okay. We'll turn it in on the Monday that I'm not here in class. But if you have some questions next time, you can ask them in class or whatever. We'll do the group work in class next time. We'll start 7-3, maybe even finish 7-3 in class next time, and so that we're not like racing like a whirlwind to try to get through everything. That's not my goal. Okay. So we will do group work for this next time. A student tries to calculate 999 thousandths to the 10,000 on a calculator and finds the answer to be 4.5173346 times 10 to the negative fifth. The student wonders how it could be that a number like 0.999, so close to 1, when raised to a power, could result in a number so close to 0. Okay, so do you see her question? Like 1 raised to any power, if the number would not have been 0.999, but had just been the number 1 raised to the 10,000th, well, 1 raised to the 10,000th would be 1. So why is it that we took off 1/1000th of a digit, and all of a sudden now we're close to the number 0? So we're actually going to do this with your calculator. So grab your calculator out. Look at this. Look, I've got 3 calculators up here. It's fun. All right, so you're going to need to write and you're going to need to type on your calculator both. But first of all, write this down. What we're going to do first is to consider just taking that 0.999 and squaring it. Okay? So in your calculator, do 0.999 squared. When you do that, you should get 0.998001. Okay, so just making sure. Did everybody get that? Yeah? Lovely. So when we squared it, it got smaller, right? I mean, not like a lot smaller, but a tiny little bit smaller. Okay, and so we're going to continue this process. So just write down square again. Everything else we're going to write down for the next several lines is just numbers. So we're going to take this and we're going to square it again. Actually, let me write it. Let me just write it like that. So in your calculator, whatever you have already, the 0.998001, if you just hit square, it'll automatically square it again. Okay? So if you square it again, you should get something like this. I'm going to write 6 decimal points every time. Otherwise, we're going to end up writing a lot. So we've got 0.996006. By the way, what that is that is the same number that we started with squared twice, which means we've raised it to the power 4, right? Because we've squared it twice. And we're going to square it again. So we've got 0.992028. And if we square it again, we've actually raised it now to the power of 8, because 4 times 2, my exponents, was 8. So I don't know about you, but this is not getting that much smaller. Are you with me? It's just not, right? It's not getting that much smaller. Let's do it again. Okay, so now I have 984119. This represents 0.999 to the 16th. I lost a penny. I mean, really, right? It's the hundredths place. I lost a penny. My 6-year-old would be very disappointed. She loves pennies. All right, square it again. And if it weren't bad enough to lose 1 penny, now you've essentially lost 2 in the hundredths place anyway. Raised to the power 32 now, because we're doubling the exponent every time. Promise we're not going to do this all day, but we're going to do it a few more times. So square it again. We have 0.937975. And that's 0.999 to the 64th. Okay, so it jumped down a bit more, right? Like a chunk. It was barely moving at first, but now it's jumping a little bit bigger every time. Agreed? Okay, because it's compounding itself, right? It's compounding because every time, it's not like I multiplied by it 2 more times. I've multiplied by it 4 more times, and then 8 more times, and then 16 more times, and then 32 more times I've done it, right? I'm doing it a lot at once by this simple squaring feature in your calculator. So we're going to do it, I think 4 more times, maybe 3, something like that. I'm going to make my screen just a little bit smaller because I'm running out of space. Okay, so if we square it again, we're finally out of the 90s. I have 0.879798. And this is 0.999 to the 64 times 2 is 128. And then, lo and behold, the next time we're actually into the 70s, 774043. This is 0.999 to the 256. Two more times. 0.599142. This is 0.999 to the 512. The last one we're going to do on this exercise is 0.358971, which is 0.999 to the 1024. I'm stopping there for a couple reasons. Number one, we've seen how significantly it's decreasing now, right? It's just becoming significantly smaller each time. The other thing that we can see is that my exponent is at 10,024, and 1,024, and I'm trying to get up to 10,000, so I'm sort of like 1/10 of the way there, kind of a perspective, right? So what's happening here? I mean, they're getting smaller every time. Agreed? Yeah, they're definitely getting smaller. So what's the deal? What's happening? Well, whenever you multiply by a value between 0 and 1, your product becomes smaller. It's smaller than what you started with. And here, we are doing this $10,000 times. By this, I mean multiplying by, I'll say less than 1, but we recognize that's between 0 and 1. So I'm multiplying by something less than 1 10,000 times. So it has this sort of a compounding effect that eventually it just keeps getting smaller and smaller and smaller and smaller and smaller as I go. It's a strange feeling though, right? To take something that's so close to 1, multiply it a bunch of times, and end up so kind of far away from 1, really, by comparison to where we began. Okay, so let me remind you again, this is not due next time, so please don't do the group work anyway, so that you have a chance to do group work with some people in class. If you want to start the homework, that will be totally fine. That way you can ask me some questions. We'll do those questions at the end instead of at the beginning. And we will also jump in and start 7.3 next time.